We are in this chapter 16 still. We're able to cover 3 topics. We introduce the energy, electric energy, electric potential energy, and also come with that potential. Okay, it's not potential energy, potential, which is defined in terms of potential energy. Then we looked at charge conductors, and we saw that charge conductor is a equipotential surface in the sense every point on the conductor, which is in electrostatic equilibrium, it will be at the same potential. And also inside will also be that same potential. This is a property of a conductor. We didn't quite finish that topic. There are some more slides left in that. Then we will continue to the next topic. So let me go where we stopped. Right, so this is it. We talked about the charge conductor. We saw that its surface is an equipotential surface. Then we introduced this new unit for measuring energy at atomic scale called the electron volt. That's where we stopped. So now we are talking about the equipotential surface again. What is an equipotential surface? Equi mean equal. So equipotential mean equal potential. So if we can have a surface and every point on that surface has the same potential, we can call it equipotential surface. So that's what it means. An equipotential surface is a surface on which all points are at the same potential. So this means we don't need to do work to move a charge, provided we move it constant speed or maybe 0 speed, so we don't change the speed. There is no change in the potential energy, so that means we are not going to do any work to move a charge from point A to point B along an equipotential surface. And we should also know that this means the electric field at every point on an equipotential surface is perpendicular to the surface. So that will guarantee we will be not doing any work. Because if the electric field is perpendicular to the displacement along the equipotential surface, that is true, then it will do no work. So this way we can figure out how to draw the equipotential surface for any electric field. Let me look at the electric field from a point charge. So these orange lines are the electric field lines. You know that, right? A point charge, electric field will be away from the charge, so radiating outward, radially outward. So these orange lines are the electric field lines. Then we can say, if I take a sphere, say this sphere, centered around this charge, although it's a 2-dimension, it's a circle, but you need to imagine a sphere. You left something? There was a class B. So there's a sphere. On this sphere, the electric field line is perpendicular because this is centered around the charge, which is at the center of that circle or the sphere. And you can see the electric field lines are at any point, it is perpendicular to that sphere. Okay, that is true, right? So this means we have an equipotential surface because on this sphere, say from point A to point B, if you move along the sphere surface, spherical surface, there will be no work done because at any point in that path, electric field is perpendicular to the displacement. That means the work done is equal to 0. So that tells me it is an equipotential surface. Because if the work done is 0, means the potential at A is equal to the potential at B. So this way we can easily draw the equipotential surface simply by, say, let me come here. So I draw a perpendicular to the electric field, and there will be electric field here perpendicular to the electric field. There will be electric field going like that, and keep doing this. Then we will end up with another sphere, which is another equipotential surface. Of course, this will have a, so closer to the charge, the potential value at that equipotential surface may be say 10 or let's say 100. As you go away, the potential will decrease. So this potential may be, let's say, 50, and this may be, say, 40. Different value, but each sphere is an equipotential surface. Now we have another combination of charges, so therefore it produces a different electric field line. This is called the dipole. Now we talked about dipole before. You should know what a dipole is. A dipole is an arrangement of two charges, one positive, one negative, but the same magnitude. So if one of them is, the positive charge is plus 2 coulomb, the negative charge will be minus 2 coulomb. So this kind of arrangement, combination of charges, is called an electric dipole. Two charges, same magnitude, but one is positive, the other one is negative. So this is the field line. So we apply the same principle. You want to find the equipotential surface, then you take this the electric field line. So here we have electric field line, draw a perpendicular to that. Then you go to some close to it, draw the perpendicular to that, and a perpendicular to that. Combine all this, then you have this surface. It's not exactly a sphere, excuse me. Move to the other chair, please. It's not exactly a sphere, it looks like an oval shape. But this equipotential surface become more and more of a sphere as it come closer to the charge. On this side, the same thing. What about in the middle? If I draw a line exactly in the middle, so it's a line in this two-dimensional picture, but it will be a sheet, plane, a sheet that exactly divide the two charges in the middle. It's also an equipotential surface. That is not a sphere, but it's a plane sheet. Any point along this plane, the potential will be zero, exactly zero. The potential here will be on this plane in the middle, it will be zero, because any point on that sheet, it is equidistant to the charges. This charge, if it has a potential of say 100 at this point plus, and this charge will have a potential of negative 100. So when you add them, the potential will be zero. So the sheet in the middle is an equipotential surface with the potential equal to zero. And as you go to the other side, it will become more of a circle or an oval, having different values of potential. To the right side, it will be positive potential sphere. On the left side, it will be negative potential sphere. Now we are looking at some applications of electrostatic energy, electric field. One of them is this electrostatic precipitator. So in industries, in factory, you know, it emits toxic gas. So we have what is called electrostatic precipitator, which reduces this air pollution. This is how it looks like. And that's this chamber body, which is connected to the positive terminal, and there's a wire in the middle, which is connected to the high negative voltage. So air around this wire will be ionized. It will electric discharge, so it will ionize the air. When the dirty air that comes in from the factory, the industry, this dirty air will ionize near this high voltage negative wire in the middle. So these which are becoming negatively charged, this particle, it will accelerate to the outside body because relative to the negative charge, this is positive, so it will be accelerating. The wire is negative and the body is at zero potential, but relatively it is negative. It will be accelerating to the body and will deposit on the walls of this instrument, and it can be collected by opening this thing here. So this way we will purify the air. The bad gas or the toxic gas will ionize and it will be collected on the body and it will be taken out. So this is an application, an industrial application, air purifier. It is called electrostatic precipitator. Now the same version of that purifier we use at home also. There it is called a smaller version, electrostatic air cleaner. It is the same principle. So it helps us to clean the air in home. Another application, Xerox machine or the photocopy machine. Photocopy machine or the Xerox machine, they use a material called photoconductive material. You know what a conductor is? Conductor is which conduct electricity, where the free electrons can flow in response to the electric field. That's a conductor. But what is photoconductor? You know the words meaning photo here? Not the picture. You know what is photon? What is it? Light, when considered as a particle. So the photo here is light. So when you say photoconductor, a material which is a conductor when exposed to light. When it is in dark, it's an insulator. So it's a very useful thing. So this is one of the applications using the photoconductive material. Photoconductive material is a poor conductor of electricity in the dark, but becomes a good electric conductor when exposed to light. Selenium is such a photoconductor. So we have selenium. This is what you see inside of a photocopy machine or Xerox machine. We have a drum which is rotating. Excuse me, please put your phone away. Put it away, please, in your pocket. So this selenium is positively charged and we spread on this drum, coat on this drum. It is coated on this drum which is rotating. And the drum is in the dark initially, okay? There is no light. So the selenium, which is a photoconductive material, is not a conductor. Now it's an insulator because it's dark. So this charge will stay where it is. It will not become neutralized from this drum, which is a metal. But then you shine light. When you shine light, this material is a conductor now. So it will be neutralized. These positive charges will be neutralized from the electrons coming from the metal, from the drum, and it will become neutralized because the electrons can move because it's a conductor now, because the light is shining on it. But the way we shine the light is through this, say, the letter. We want to print this letter, say the material. So it's dark, right? So there will be no light going through this place, okay? So there will be a shadow here, like the letter O. Those places where there is shadow, no light is shining, it will not be a conductor. The selenium will be an insulator. So if it is an insulator, these charges will not get neutralized. Those charges will not get neutralized because electrons cannot move in that area. So this will be saved. This selenium will stay, this part of this selenium, like the image of a letter O, it will not be neutralized, it will be charged. Now then in the photocopy machine, you have what is called toner, like a black powder that you put in. This toner will, it's a charge toner, so it will stick to this positive charge only in these places, because here there are no charge. Because a charge toner, it will go to the positive charge. Maybe it is negatively charged, it go to the positive charge, it will stick there. So what do we have there is an image of that letter O. Then you transfer that thing to a paper, so you have a print, a copy of that letter O. So this is the mechanism of this Xerox machine using the photoconductive material. So in a laser printer, it's also copier. What is the difference is you don't have a light shining like that, but instead we use a laser beam which will be scanning that rotating drum. So it will get the signals from the computer, so it will scan such a way that it will make a letter O on the drum. Okay, it will shine. When it comes to this plate, it will be off, then on, so it will just make the image O. Right, that's what I have described now. That finishes, we just gave some applications of this electrostatic field or conductor. Now we come to the next topic, capacitor. So we said this title of the chapter is electric potential energy, electric energy and capacitance. So that's where this capacitor comes in, capacitance. You know about capacitors because I told you about capacitors in chapter 15. What is a capacitor? Just two plates with a gap. So parallel plate capacitor. These are conductors, these plates are conductors. And we keep it very close, but don't touch each other. There's a gap, a small gap there. And if I connect this capacitor plate, one side to the positive terminal and other side to the negative terminal of a battery, what happens? What happens when you do that? Will there be a current? Why not? Because there's a gap. Yeah, there is a space, right? So the current cannot flow continuously, but there will be a current for a brief period of time. What happened? So what is current? Current is flow of charges. So the battery has separated the charges. Now there are positive charges here, negative charges here. So the positive charge will flow. Actually, it's always the negative charge which is flowing, but let me just say the positive charge flow and come here. There's gap. We cannot jump. There is no wire between the two plates. What is in between the plate? Air. Can charge flows through the air? No. Air is insulator. It's not a conductor. Cannot flow. So that positive charge will be stopped. So this plate will see the repulsion, the electron here, okay, positive charge here, okay, but actually positive charges do not move, it's only the electron which is moving. But to explain this, I'm going to say, okay, a positive charge here will feel the repulsion from positive charge in this plate because now it's charged by one positive charge. It will leave and come to the battery. Although there is no connection here, you see there is a flow of charges. But this is not going to happen continuously. Why? Another charge will come, another charge will leave, so this will become. So when a positive charge leaves, this will become negatively charged, right? So one positive, one negative. Second positive charge come, and a positive charge will leave, this will become negative. Third one will come, it will feel the repulsion, the positive charge, it will leave, so it will be another negatively charged. And this process will continue. Not forever. Why? The charge separation is the one make this, say this battery is 12 volt. So when the charges are accumulating in this capacitor, this is also going to have, this capacitor will have charge separation. So this is also like another battery. But this guy wants to send the current in this direction. Positive terminal, the current will go and receive at the negative terminal, it come back. Current will flow like that. But this is also now like a battery. You have a positive terminal here, negative terminal here. So this will try to, send the current this way from its positive terminal back to its negative terminal. But it is not charged, there is no as much separation of charges as in the battery. So I can just put some numbers to explain things. Say now it will become like a 3 volt battery. This is 12 volt battery trying to send the current this way. This is a 3 volt battery trying to send a current in the opposite direction. So he will win, right? Because this is higher potential. So it will keep sending more charges. This become negative and more and more. At one point, because this is also now collecting charges, the potential here will be now equal to 12 volt. At that point, the current will stop. No more current. At the beginning, as you put the switch on, there will be a big current, then the current will reduce. And when the capacitor has the same potential difference across its plates as the battery voltage, no more current, it will stop. So initially there's a transient current, okay? It will happen in very fast, like maybe less than a second, a fraction of a second, depending on the capacitors and the resistors in the circuit. So it will build up charge. The potential difference across the capacitor plate becomes same as the potential difference of the battery. Then the current flow will stop. And this will happen very quickly. Now, for these capacitors, we define something called the capacitance. The symbol is C. The device is called capacitor. And we define a capacitance for this capacitor. How do we define that? It depends on how much capacity it has to store charges on it. So that is why the name capacitance. You know what is capacity means? The word meaning of capacity. Yeah, how much it can hold, okay? If you have a bucket, small bucket, its capacity, you can say 2 liters. If you have a big bucket, you can say its capacity is 3 liters and so on. Similarly, this place, how much charge it can store in it. So we can, per the voltage difference that you give. So you connect a 12 volt, it can store maybe 5 coulombs amount of charge. But if you connect the same thing to a 24 volt, obviously it can double the capacity. So this capacitance is going to be, it's defined as the charge on one of the plates, is the same charge, right? If it is plus 3 coulomb here, it will be minus 3 coulomb. So charge on any one of the plate, the magnitude of the charge, divided by the potential difference across the plate is called the capacitance of the capacitor. So that is we define. So we have the formula here. C is equal to Q over delta V is what is the capacitance of a capacitor. Is defined as the ratio of the magnitude of the charge on either conductor of the plates to the magnitude of the potential difference between the plates. So now we have learned something new. There is something called capacitor, and we can define the capacitance of the capacitor. Symbol we use for capacitance is C, capital letter C. Here it is. So what about the unit? This is coulomb and this is volt. So the unit for SI unit for capacitance will be coulombs per volt. But as always happens, we have an official name. Instead of saying coulomb per volt, we call it farad. It's the same that person Michael Faraday that we don't say Faraday, drop it and call it farad. It's after him only. Typical value of capacitors are in the range of microfarad. Farad is a large unit for a capacitance. Right. Now, I can show you a simulation of this capacitor in an app, PHYE that we here. You can, if you want, you can point your camera to this QR code, come to this. Anyway, right. So here we have a battery. Now the battery is 0 volts, so like a switch, we have switched off. Nothing on the plate, right? Nothing on the plate. There's a wire connected to one end of the plate, another wire negative from the negative terminal connected to the other plate. So if I switch it on, make it 1.5 volts, see what happened. Very quickly, on the plate that is connected to the positive, that plate will become positively charged. The plate that is connected to the negative of the battery, it will become negatively charged. It happens very quickly, okay? So there is no current flowing continuously. It just flows and stops because there's a gap here. It's not, you cannot have a continuous flow, right? You can disconnect the battery, the charge will be there. Of course, it will discharge slowly through the air, although we say air is a insulator. If there is moisture in the air, it can leak. Okay? It can discharge slowly. It will take a long time. You can even check the voltage. This is the voltmeter. So it should be 1.5 volt because we let it connect it to this end, maybe, and see what the voltage is. Yeah, it has become actually minus 1.5 volt. Okay, it will be because for the battery, it should be, why it is minus, you have to connect the positive end to the positive end because the voltmeters also have polarity. So the red is the positive end and you connect there, you have plus 1.5 volt. So this is at a higher potential like the battery here, same potential as the battery terminal, and this side is the negative. So the potential difference is 1.5 between these two ends of the plate. Right. I can also show with this bulb, now what we have here, a battery, but it is 0 now, so let me bring it. So it is charged. Now what do you think will happen? I take it and connect these two plates via the bulb. If I touch this, you have a circuit completed. Now this is like a battery now. So that will make the bulb lights up. There will be a current that flows through the bulb, but it will last for a few seconds or few minutes, depending on the value of the capacitance and so on. So let me show it, just connect it and see what happened. So it will be very bright at the beginning, large current, then slowly the current, it will be neutralized, it's flowing, and then no charges on the plate, and therefore now no more current through the circuit. Okay, now let me go back to this. Right. So we said the definition of the capacitance is the magnitude of the charge on one of the plates, because they are equal in magnitude, divided by the magnitude of the potential difference. That's the definition of the capacitance. Okay, right. Now, the capacitance really going to depend on the geometry of the plate. Again, let me go back to the simulation. I'm going to use this. Let me connect it to the battery. So let me start with no charge. Now I switched on, so there is charge. It has stored some amount of charge. Now tell me what will happen to the amount of charge if I increase the area of the plate. Keeping the same voltage, the potential difference is the same. Okay. Now, if I increase the plate area, can it accommodate more charge? Yes, right. I mean, because it is like a more area, it can accommodate more charge. Let me, right? It is going to have more charge. So now you see the capacitance will increase proportional to the area. Okay, that kind of makes sense. Okay, because it has got more area to accommodate more charges to come and reside there. So like people coming to live, so the charges are coming to live on this plate. Right, so that makes sense. So you can see that the capacitance is proportional to the area. Now another question. If I change this gap, say let me call this is D. Usually you keep it very close, right? Suppose I increase the gap, what do you think will happen? The charges will increase, number of charges will remain the same? Increase or decrease? If you increase, it will decrease, because the electric field influence from one plate to the other, because there is a more distance between them. So it will not be able to accommodate as much charge if you increase. Let me just demonstrate it. So its number of charge become less, right? If I D increases capacitance, because capacitance is how much charge per unit potential, right? The given potential. So I'm not changing the potential, I'm only changing this distance. That will change the number of charge. If I bring it closer, it can accommodate more charges. So that's what we have here. So you can see this C is directly proportional to the area, but inversely proportional to the gap distance, the distance between them. And we can prove this exactly from, but I'm not going to do that. The same constant that comes in here. Now, when you have a proportionality equation, you're going to have a proportionality constant that happens to be the same epsilon zero that comes in the Coulomb constant, which is called the permittivity of free space that comes in there. So this is not the definition of capacitance, but how we relate the capacitance to the geometrical properties of the capacitor plate. Right. In chapter 15, we saw that for a capacitor, we start with the ideal capacitor. What's an ideal capacitor? Which has an infinitely large area. Two capacitors which is huge, okay, infinitely large. Then we say the electric field inside is constant, uniform, and it is given by this formula. So these are constant depending on the charge density. This is a charge density, this is a constant. So the electric field inside is this much, a constant value. Outside it is zero. This is an ideal capacitor. Ideal capacitor means very large capacitor, infinitely large, two plates. But in reality, we don't have ideal capacitor. We have capacitor of finite length. But we can still say near the center, we more or less have a uniform electric field given by the sigma of epsilon zero. But as we come to the gap, the opening, it will become weak. And outside we said it is zero, but it is not exactly zero because it's not a infinitely large conductor, capacitor plate. So you will have some very weak electric field, even outside. But you can still take it as at the center of the capacitor. The electric field is uniform and given by the formula sigma over epsilon zero. Some applications of these capacitors, very simple application, camera flash. Because, we can have a capacitor inside the camera, which will be charged by the battery of the camera. So you have a capacitor, which is like another battery because we have charges, positive charges on the one plate and negative charge on the other plate. So it is ready to give out the energy if we connect it to a bulb, so LED bulb or something. So what happens now? In the capacitor, when it is charged, one is positive charge, other one is carrying negative charge. It's like a battery. So we have it ready when we can have it charged to very high voltage. So you can give this energy very quickly to a bulb. When you connect it, when you press the button of the camera, the flash button, the charges will be released and it will go through the bulb and you have a light, the flashlight. So this is one application of capacitor. The energy stored in the capacitor is released when the button is pushed to take the picture. The charge is delivered very quickly, it doesn't last for long. It will be very bright light and then it is gone. That's all we need for taking a picture. Another application, the computer keyboard. Let's look at this key, the particular key, say, which has the letter B. And it is standing on two plates. These are capacitor plates. And between the capacitor, it's not air. Air is an insulator, so it needs to be a gap, right? It should be electrical gap. We can have an electrical gap. Even if you put something which is an insulator. As long as this is an insulator, it doesn't have to be nothing like air. Air is also insulator. So that's why the charges cannot cross that. Even in an insulator, like rubber or mica, there are many things we can use. It is an insulator. But in the context of capacitors, we call it dielectric. It's an insulator, but it's a special name. When you keep an insulator between the capacitor plate, we call it dielectric. Okay, it's an insulator. Insulator means not a conductor. So the current cannot pass through one plate to another plate because of that insulator. So it is effectively another capacitor. Now, why we do that? Because with air, we cannot do that. Now, when you press the key, this is fixed plate and this is a movable plate. When you press the key, what happens to D? Decreases, changes, right? So what will happen to the capacitance of this capacitor? It will increase. The capacitance will increase. So that will be a signal to the computer because of that connection. There are electronics there. So it knows which key is pressed. It's because it can detect the change in the capacitance happened in the capacitor that is fixed to the letter B. So, right. So that's how it detects which key is pressed. So another application. So we have finished introducing the capacitors. Now we will see what happens when you connect a capacitor in a circuit. Capacitor is very important circuit element, like as much used as a resistor. You know what a resistor is? Probably. So, let me draw a circuit diagram. I draw something like that. Do you know what this is? It's a symbol for a battery. Now you have to remember this, okay? Now, please don't forget it now. The large line, long line is the positive side of the battery, and the short line is the negative side of the battery. This is a symbol for battery. Then wires, we need wires, right, in electric circuit. So this is a wire. And you may have something like this. What do you think this thing is? Switch, key, okay, key. So you connect, if you want to connect the circuit, you come like that, okay, you can make a continuous wire. So now the continuity is lost. So it is the switch or key, some people call it key, okay, switch. So this is a symbol for a switch. What do you think this is? Guess? It's not the same as that, right? This is a battery. Capacitor. The capacitor consists of two plates, right? So one equal size, that is capacitor. This is symbol for capacitor. Then you take some more wires and come back and connect to the battery. We have an electric circuit. This is a circuit diagram of an electric circuit. Right. So what happened now? From the battery, the energy will be drawn because it can send a current. So electric charges will be moving. So it is transferring energy from the battery to other components in the circuit. So this kind of diagram you should be able to read correctly. Circuit diagram can be used to show the path of a real circuit. Now, is this a circuit diagram? No, we should use the symbol, right? So actually, if you want to draw the circuit diagram properly, you don't draw the picture. That's not practical. So you put it like that. And then this is a capacitor, you put it like that. Then there is another capacitor, you put it like now we have a complete circuit diagram. So that is kind of, we are drawing the pictures of the thing rather than putting the symbol. Now we say when you connect two capacitors in this manner, we say this is connected in parallel. These two capacitors are connected in parallel. You can see by looking at, okay, it is one above the other, looks parallel, right? It's not about the look. It's deeper than that. It is not just the look of it. Why do we say it is connected in parallel? For both capacitors, we apply the same potential difference, the potential difference of the battery. So this point and this point are at this is a wire, it's a conductor, superconductor. You can say there's no drops of potential. The potential here, the left plate, let me use the red plates of these two capacitors connected to the same potential. The battery, say this is a 12-volt battery. So if the positive side is 12, the negative side is 0. You can put it like that. So the potential here is also 12. The potential here is also 12. What about the other side? The blue side. This is 0 means this is also 0. This is also 0. So you can see the potential difference across the capacitor plates, both of them is the same. The potential difference across C2 is 12 volts, the battery voltage. Across C1 is also 12 volt battery voltage. When we have that, we call it these two capacitors are connected in parallel. So if you put it the other way around, if you want the two plates to be connected in parallel, you make sure you apply the same potential difference across both of these capacitors. Then it is connected. It's not just the look, okay? It's what is important here is to understand the same potential difference is applied across both these capacitors by one battery. When capacitors are first connected in the circuit, you know what happened? I described the electrons. Actually, the electrons, the negative charge which are moving, transfer from left plate to the battery to the right plate, leaving the left plate positively charged and the right plate negatively charged. Okay, so electrons will go like that, come here and stop. So the left plate will be negatively charged and the electron will leave from here, that will make this positively charged and so on. But this flow will not continue, it will stop at one point. when it is fully saturated, it will come to the same voltage as the battery voltage, it will stop. So it is transient, it is not a continuous thing. So here we have drawn it schematically with the symbol. Someone can ask now, can I have two capacitors connected in parallel. Can I substitute these two with just one capacitor? I'll call it equivalent capacitance, which does the same thing as these two capacitors together. If so, what should be the value of that equivalent capacitor? Say, for example, this is 2 farad and this is 3 farad capacitance. So this should be what should be the one capacitor which will do the same job as these two capacitors. So you are saying they add them, 5, make a 5. That's what you are saying. Yeah, you are correct. Okay, so that is the final result. We are going to prove it. Okay, we are going to prove it. You can kind of understand because this guy is going to collect charge with the same potential. This guy is also collect charge with the same potential. So two people are working. So if you want to replace that by one person, that person should have the same capacity as the two people put together. So his capacity is 2, this capacity is 3. So this guy better have a capacity of 5. Makes sense, right? We can prove it mathematically. How do we prove it? So in both of them, we apply the potential difference across this is delta V1, which is equal to delta V, the battery voltage. If I call it delta V2, it is also equal to delta V, that battery voltage. So I can write this. The potential difference across capacitor 1, if I call it delta V1, it is equal to the potential difference across capacitor 2, which is delta V2, and equal to the battery voltage. Now here we have the same battery voltage. The potential difference across this is also delta V, same as the battery voltage. Okay, now can I say these two charges are the same? Charge on, no, they are not the same because they have two different capacity. So the one with the bigger capacity will have more charge, one with the less capacity will have a lower charge. But you can say this, right? The charge that is coming from the battery, which will be deposited in this equivalent capacitor as well. This Q, the combined coming from the battery, it will be divided into, some of them will, Q1 will go to capacitor 1, Q2 will go to capacitor 2. Therefore, the total charge coming from the battery is equal to Q1 plus Q2. Now we know, maybe I'll go to the next one. So you got this equation, this equation. What is the definition of capacitance? Q over delta V. That is the definition of the capacitance. So for C1, it will be Q1 over delta V. Do I have to put delta V1? No, because delta V1 is equal to delta V. Okay, so and similarly, C2 will be Q2 over delta V. And I can say for the equivalent capacitance, it will be Q divided by delta V, not Q1, not Q2, but Q, the total charge, the whole thing will be in that one capacitor divided by delta V. Now see what happened. For Q, I can write C equivalent delta V. For Q2, I can write C2 delta V. For Q1, I can write Q1 C1 delta V. I don't have to put delta V1, delta T2, they are all equal. Now you see these are equal, they cancel. Very simple proof. So we have proved the equivalent capacitance when you combine two capacitors in parallel, it will be simply the addition of the two capacitors. Do you need to prove this? No, because I cannot ask you a question in a multiple choice, prove, right? So you don't have to know how to prove it, but it is nice if you know how to prove it. Otherwise, you can just remember that. Okay, memorize the formula. Even if you forget, no problem, it is in the formula sheet. What if you have more than 2? Just keep on adding. Just keep on adding. Simple. That's what he's saying. Right. Now what is this? Is this in parallel? Not at all. Because this, suppose this is 12 volt, and depending on, this delta V1 is not going to be delta V2, because they are one after the other, just in series. We call this connection capacitors connected in series. But we can say this is the other way around. In parallel, we said total charge is equal to charge 1 plus charge 2. It's the opposite. Total voltage, the voltage from the battery will be equal to delta V1 plus delta V2. Okay, just simply add the voltages one after the other. That will be the total. On the other hand, what about the charge? Same charge, Q, Q. Because in series, whatever the charge that flows through capacitor 1 has to, there is no branching, right? No branching, unlike the parallel connection. So same Q in both plates. So now we can get that and prove the equation. Is it proved now? Let's prove this now. Okay, now I have this. For delta V, because capacitance equation is Q over delta V, is the equation. So delta V will be Q over C. For this guy, I can write in terms of the equivalent. I will replace these two by just one capacitor, C equivalent. And this is the voltage delta V. The whole delta V is appearing across that. So for the delta V, I will write Q, right? It is the same charge, Q divide by delta V for the equal, sorry, C equivalent. Delta V is equal to Q divided by C equivalent. Yeah, I'm just using this equation, and delta V is Q over C. So this whole voltage is applied across the equivalent, and the charge is also Q. So delta V can be written as Q over equivalent. What about delta V1? I will write Q over C1. Delta V2, I will write Q over C2. Now what happened? Q cancels. And what we have, the equation is 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Right. That's nice equation. I will skip this because I was talking about it only. Right. Here is the proof. Now this equation, I would like to put it in this manner. So 1 over C equivalent is equal to C1 inverse plus C2 inverse. You know what is to the power negative 1 mean? Really mean 1 over C1 plus, yeah, it inverse it, right? So this is 1 over C1. You can write it as C1 inverse. So C1 inverse actually mean 1 over C1. So I put it like that. So if you want to get the C equivalent, what do I do? Take the inverse both sides. Because you are going to use the calculator, right? You don't have to do common factor and things like that. So since we are going to use the calculator, this is the best way to look at it. The equivalent capacitance is equal to sum of the inverses, and take the inverse of that. It will give you the equivalent capacitance when they are connected in series. Now we are ready to do questions. Okay, but then what if we have more than 2? Just keep on adding. Okay, the same thing, keep on adding. Right, now these are the problem solving strategy. Let's not just read through it, let's do the question. Okay, we have an example question, so let's do this. How do I get the capacitance between these point A and B. Between this A and B, we have a complex combination of capacitance. Can you come, the three of you come to the front, please. Stand up, please. Come to the front. The moment I look away, you are talking to each other. Now help me to solve this problem. Ready? Okay. Right. We have how many? We have so many. Which one you are calling? Let me call by the value. Say this is a 4 farad capacitor, 1 farad capacitor, 3 farad capacitor, 6 farad, 8 farad. It is connected. Can you tell me which one is parallel connected? Or series connected, let me say. Series connected. Yeah. Can you name 2 capacitors that are connected in series? 8 and 4. You don't have 8 and 4. How come they are 8 and 2? These two you mean? Okay. Not 8 and 6? 3 and 6. You mean they are not even connected. None of them are connected in series. Connected in series means they should come one after the other without any branching. This is in series. If you say that somebody told me these two are series connected, maybe you are looking at like this. But at this point, it is branching. So this and this is not series connected, because series connected means whatever the charge that goes through this must be on this as well. So it is not connected in series. Can you tell me if there is any two connected in parallel? Whatever is circle, right? That is, I mean, quite obviously, that is why it is put it in the circle. And this guy, these are put in the circle. That means those two are, for sure, no doubt, they are connected in parallel. So the way we do this question is go slowly, one step at a time. So I can recognize this combination connected in parallel, this combination connected in parallel. Let me go to the next slide because it's done nicely. So I know these two are connected in parallel, and separately these two are connected in parallel. So what I will do, I will reduce this to just one capacitor. So there are two here. I will throw the two of them and put one equivalent capacitor. You know what should the value of that equivalent capacitor? This is 6 and this is 2 connected in parallel. So the formula is add them. So that's what you learn, right? In parallel, you have to add them. So 6 plus 2 is 8. Okay, right. And these two, 1 plus 3 is 4. Done. We are not finished because we have to reduce everything to just one capacitor. So the next step, now I can recognize this two, the equivalent capacitor that we got and the one in front of it, these two are in series. 4 and take the 1 over of the whole thing, right? This is, I would like to show this with the calculator. right? The best way to do is as follows. So the equation is take the 1 over C1 plus 1 over C2, then the inverse of the whole thing. So 4 inverse, this means 1 over 4, right? This means 1 over 4 plus the second guy, 4 inverse. That's all. So 1 over 4. Let's do this first. So what you are getting is not C equivalent, but 1 over C equivalent. Keep that in mind, okay? Don't miss that point. So let me press the equal button. So this is 1 over C equivalent. So what do I do now? Take the inverse of that. Okay? So that's how. Have you noticed something? Oh no, let me do the next one also, then I'll ask that question. So this guy, let's do the same thing. 8 inverse plus 8 inverse, get the answer, and take the inverse of that, 4. Did you notice something here? Yeah. So we have a shortcut. If you have identical capacitors, if the capacitors have the same value, if there are 2 of them, we take the half. If there are 3 of them, divide by 3. If there are 4 of them identical, take one of the value, divide by 4, and so on. So this is shortcut. You don't really have to do calculation. So now we are here. Now here we have no such shortcut. I mean, it's an easy one. They are in series, they are in parallel. Simply you have to add. 2 plus 4 is 6. We are done. Okay. Right. So this will be my last slide. So when we have a capacitor plate, you store electric energy because you put charges in here. It's like a battery now. It can send current if connected to something. So it is storing electric energy. And we have a formula for the electric energy stored in a capacitor. We call it U. This is the formula. We can prove it, but I will spare the trouble for you. You don't need to know how it is proved. You just remember the formula. Electric energy is stored in a capacitor which has a charge of Q, and the potential difference across this is delta V. You just simply use this formula to calculate the energy stored in a capacitor plate. That's it. However, okay, this is the first equation. You know, capacitance is given by this. It's the definition of capacitance. So what I can do, if I take this equation, I know Q is equal to C delta V. I can eliminate this guy by substituting C is equal to delta V. What do you get? You get this. Okay. Because it's become useful sometime, because maybe in the question you will be asked to find the energy stored, but the guy only gave me delta V, but he didn't give me Q. Instead, he gave me C. So you don't bother with this equation. You jump to this equation and calculate the stored energy. I can do another thing. I can eliminate the delta V. Say maybe delta V is not in the question. So delta V is equal to Q over C. I can take this and put it in this guy. Then I get this one. Suppose there may be another question where he gives the charge. He doesn't give the voltage. He doesn't give. He only gives the capacitance of the capacitor. So use that. Okay. So that's why we mention all 3 equations. Okay, I will stop today. You know, the exam is next Thursday. Okay. Please prepare. We have some more slides left, not much. We can finish it quickly in the next class, and then we can start solving questions. Okay.